Okay, good afternoon, everyone. So thank you for coming to the tutorial. So let me introduce you to Sanja Stajner. So Sanja did her PhD in Wolverhampton a few years back. Also, she did a postdoc at the University of Mannheim, and now he's working for this company, Simanto, on personality detection, as far as I understood. Yeah. So a lot of exciting stuff on natural language processing, and I am Horacio Saggion from this house. So most of you know who I am. So this is more information about ourselves, so if you need to check. And there are several antecedents for this tutorial. So I gave part of this tutorial a few years back at the joint conference in natural language processing. So in 2013, there was not much deep learning at that time. Then I did a tutorial in RunLP a few years later. Then Sanja did a tutorial on RunLP with more up-to-date approaches, and then we decided to merge both things for last year calling tutorial. Also, part of the material that I myself cover in the tutorial is from a book on text simplification. And that's it for the moment. So we'll start with the topics. So we will have, I will be talking first on the more boring and traditional stuff, introducing the concepts, introducing traditional systems, and then Sanja will give you all you want to know about the neural machine translation and neural approaches to text simplification. Okay, so that's the idea. Also, Sanja will take the word at some points to clarify stuff and so on. Okay. So the outline of the presentation will be, first we will motivate a little bit why we need text simplification for. Then a few approaches to text simplification. We will see some full text simplification projects that have been developed over the years. We'll talk about something very important, that is resources that exist for text simplification. This can be corpora, dictionaries, and so on. Then we will see neural text simplification and fully fledged systems, so systems that go from the beginning, do everything that has to be done to the text to transform it into an easier version. Okay, so first, motivations for text simplification. So first, text simplification, what is it? It's the process of transforming a text into a version which is equivalent, but will be easier to read and understand by a particular target population. And the idea is that during text simplification, sentences which are long and complicated will be split and transformed into shorter sentences, and sentences which contain a complex or uncommon vocabulary, this vocabulary will be transformed somehow to make the text easier to read and understand. And there are several operations that occur during text simplification. These operations can be at the lexical label, could be at the sentence label, and can also be at the discourse label. And in natural language processing, it started to call attention of the community more than 20 years ago, but not as a tool which could help people, but as a tool which could help our own natural language processing people. So as a pre-processing step for different tasks in natural language processing, such as information extraction or question answering, or you name it. Okay, so why we need text simplification? Well, we know that we are facing with the democratization of the access to information online. So we have access to incredible amount of text. So the internet has democratize the access to information, but not all the information is equally accessible to different people. So there are texts which can be very complicated. So here, because they contain long sentences or because they contain complicated vocabulary. And this is one example of a source that is Wikipedia, that is should be accessible to everyone. And if you take the definition of opera in Wikipedia, so the first sentence that you get is this one, which is a long sentence, maybe not too long for us, but contains complex vocabulary such as the words libretto or musical score and so on. It has also some kind of subordination. There is a resource that exists also that is called easy text usually will not contain this type of sentences, will contain shorter sentences and common vocabulary. And usually, easy-to-read text will have this logo or an equivalent logo to indicate that this is being prepared for people who cannot read complicated texts. So if you go to simple Wikipedia and we look for the definition of opera, so you have much shorter sentences. So the definition is split into two different sentences. And you can see that there are not so complicated words. Okay, so these type of texts are texts that are needed for certain populations. There are also many more examples of simplification on the wild. So, for example, the Spanish Constitution that contains legal text. So usually the sentences will be maybe long and maybe complicated. But sometimes you get an easy-to-read version where the sentences will be much shorter and expressing paraphrases that make the text easy to read and understand. And actually, the law is something that should be accessible to everyone, or your rights, and as a citizen, should be accessible to anyone. This is an example of the lead paragraph of a news article about the closing of the Calais refugee camp. So you see that it is very complicated, and this is what usually happens with newspaper articles, that the first sentence or the first paragraph is quite complicated, packed with information. But there are organizations like United Response in the UK, which try to make information more accessible. So this is a version, not a translation, it's a version of the same news, but in a very simple language. Also, the parliament in the UK, for example, explains what the parliament is, explains about the laws, and also provide, so you can see it's very complicated vocabulary. The British Parliament, United Kingdom, British Crown dependencies, and so on, overseas territories. And they also provide versions which are quite simple to read and understand. Okay? And believe it or not, opera is something very complicated. And for example, last year and a few years back, a liceo from Barcelona had librettos in accessible format. So you could go, download the libretto, and will be written in an easy-to-read format. Okay? So also there is this. So adapting the text, a text to make it simple could be beneficial for several types of people, such as people which have language impairment, can be language impairment from the day they are born, or can be language impairment because they had some accident. Okay, could be, we may need simplified text for people who are learning a language. They may not have any problems of comprehension in their own native language, but maybe they need adapted text because they have not acquired all the lexicon or all the syntactic structures that they need in another language. And also, if you are a non-specialist in a particular domain and need to read some text from a particular domain, you will need some help, like, for example, enriching the text with additional information in order to make it simple. And as we said in the beginning, a simplification was used in some occasions as a pre-processing step for other natural language processing tasks, such as, for example, to extract information and make systems more. So either you have the sentence is simplified, and then extracting from the sentence is easier, okay? And, or you can simplify the text and make information, the selection of information for summarization easier, or you can find answers more easily for question answering. But obviously, adapting text manually is very time-consuming and requires a lot of human expertise. So we need some kind of natural language processing here to help to produce adapted versions of documents. With respect to simplification users, there have been many examples of systems we target different simplifications users. So there were studies targeting deaf people because they don't have the same abilities as people that they don't have auditory problems. So they need maybe paraphrases of the information. There has been approaches for blind people, although they may have not cognitive problems and they don't have access to the written document. There was an application, for example, to simplify text and pass it through a speech synthesizer, and then the person which was blind could decide whether the text was relevant or not for what he needed. Okay? So there are applications for people with low literacy that they cannot access probably the original text because they have not acquired all the expertise that we acquire through a school. For people with autism that have different type of problems with language, such as, for example, figurative language. They cannot understand figurative language. They cannot understand certain constructions. People with aphasia resulting from, for example, a stroke. So they would have problems with some syntactic structures like passive constructions, or with very complicated noun phrases, or with very long sentences because they don't have the capacity to concentrate. Also for second language learners, they will not have problems with cognitive problems per se, but they will have this difficulty on accessing all the knowledge that they need to comprehend language. And also dyslexic people who will have problems decoding, for example, the words of the language. And with respect to the language themselves, there have been applications for text simplification for many languages. Obviously, English is the one where you will find more work done, but there are also research in many different languages and language types. Okay, what is involved in text simplification? So there is one particular task in simplification that is called lexical simplification. The idea is that you will replace words which are complicated by simpler synonyms. Okay? So the task is not so direct and can be addressed in two main ways. So you can address the task as all-in-one problem, where you could, for example, apply a kind of machine translation system that will take the input and produce an output, and probably there will be replacement here and there. And you can approach this in a modular way. So you can have, in order to do that, what you need is an inventory of synonyms or near synonyms or equivalents for particular words. This can be, for example, a dictionary of synonyms, can be a knowledge base like, or a lexical database like WordNet, or can be also a word vector space, where you can retrieve equivalent words. You need also to decide which words in the sentence or in the text you need to replace. So for that, you need to identify which words are complex and which words are not complex and don't need to be replaced. This is usually called a complex word identification. Then you need to have a method to choose the most appropriate synonym in context. So you have a word, you have a list of synonyms, then you need to decide which synonym goes better in that particular context. Okay? And then you need a method to generate the replacement. So you will need some morphological adjustment to the word and probably some adjustment of the context. The other task that is usually addressed in simplification is syntactic simplification, where you are going to try to reduce the complexity of long sentences by transforming them in equivalent short sentences. And in order to do that, in general, you need an inventory of particular phenomena that are difficult to deal with by your target population. So it could be, for example, relative clauses, or could be conjunction, or could be different types of subordination, and so on. You need a method to identify those constructions in text, and then a procedure to be able to rewrite the sentences into the new ones and properly order the sentences to make the text cohesive and coherent. Also, discourse phenomena should be addressed in text simplification. I must say that most systems take word by word and sentence by sentence approach. They don't look at the whole picture at the discourse, but discourse phenomena should be taken into consideration. So how to order the sentences that you have produced, for example, or which connectives you are going to use in order to convey the same message as in the original, or whether you are going to deal with some coreference phenomena, because if you change a particular word here, then maybe the coreference that was there, it doesn't work anymore, so you need to repair it, okay? So discourse phenomena should be addressed. And there can be additional processes involved in simplification, such as information enrichment. Instead of simplifying, you may add definitions, yeah, or clarifications. You may summarize the information. So if you have a long text, maybe you would like to summarize it first and then simplify it, because some of your target population may not be able to read long documents, and you just need them to capture the essential content. You may involve some sentence compression, because parts of the sentence don't need to pass to the simplified text. Okay? For example, a sentence that may contain too many details, you may decide not to include it into the simplification. In some cases, you need semantic paraphrases, because there is no way that syntactically you can transform one input into another one. And sometimes you need to enrich the text with some form of augmentative communication, alternative communication, such as adding pictograms to better understand the message. And finally, also it's important how you render the information to your user. I think it's also an important aspect of that should be taken into account. Okay, so the basis for building text simplification systems, so there are different theories that you could use. You could base the development of your system in psycholinguistic theories. So for example, you could rely on when particular words are acquired by the population, so the age of acquisition of the words. You could you could learn, for example, from parallel data, so looking at which phenomena you have to model if you have parallel data, original text, and simplified documents. So you may have a linguist that will look into the corpus and decide which phenomena should be addressed. You may use a tracking paradigm, so maybe, Sanja, you would like to say something about the tracking procedures.
Okay, so there are not many studies done for eye tracking, but for example, there are some of them done especially for people with autism, when you check what difficulties they have in text. So sometimes it's much easier just to give them the text to read, and you are following by eye tracker how their eyes are moving there on the screen. And by that, you can see what are difficult constructions or difficult words. So the words that are difficult, they will spend more time there. Or also by recording the jumps, you can see what kind of sentence structures make problems for them. So that's one way of doing it. Right?
So maybe to remember that also here, I mean, Luz Rello has done a lot of work on simplification for people with dyslexia, also looking at the patterns of looking into decoding words. So you can also rely on human informants, so you can ask people to give you information about the complexity of the words, or which words should be replaced by which synonyms. And if you have a simplification for applications, usually, I mean, or ideally, you should look into what has failed in the output of the system and which phenomena in the input has made the system fail. And so you will design your system based on those difficulties. Okay, so access to information has never been so easy because of the widespread information that you have on internet. However, the way in which information is transmitted can be a barrier for many people. So I think that many organizations, in particular the government, should be careful about how information is put on their websites. And there is, I think, a considerable amount of interest, or there should be a considerable amount of interest from organizations, governmental organizations, in trying to make information more accessible. It is a real-world application, so we can see examples everywhere of text being simplified for people with special needs. And simplification should consider different aspects of the text, not only the sentences and the words that the sentences contain. So let's see what approaches are been there for text simplification. So usually text simplification can take two different main approaches. Either you can have rule-based systems based, for example, in the observation of phenomena in a corpus, or by inspiring yourself in psycholinguistic theories and so on, or you can have fully data-driven approaches that learn from parallel data, for example. Okay? And for data-driven approaches, you may have machine translation, the traditional statistical machine translation. So for a few years in text simplification, I don't know, maybe 5 years, there was a trend of using a statistical machine translation to transform a complex text into a simple text. It is a kind of monolingual machine translation. Okay, so you have a corpus where you have complex sentences, and then on the other side you have simple sentences that you learn how to transform one on the other using a statistical machine translation. And this has now been replaced by neural machine translation. Also, you can learn not how to translate the text, but how to translate syntactic trees. So you can have a syntactic tree of a complex sentence and then learn which operations you should apply to the tree in order to get more simpler trees, okay? And then generate sentences out of the trees. And you can have, obviously, a combination of both. You can have a data-driven approach for some parts of the system and some rule-based approach for another part of the system. The problem with rule-based, obviously, is that it is tied to a particular language, so you have to develop rules. You need a computational linguist to write the rules. It is difficult to port. What I must say is that the system, usually, if you have a linguist working on syntactic, for example, simplification, the system will be quite precise, so will produce good simplification. Maybe will not have the appropriate recall that the system requires, but will have a good precision. And the problem with data-driven system is that there is not enough simplification data out there. So there are several corpora available, but they are not big enough as the data that you get for neural or statistical machine translation approaches. So those are the problems that we face. Okay, so an important aspect of simplification, as in any natural language processing task, is evaluation. And evaluation in text simplification is measured in two ways. One, you can measure the quality of the output that the system is producing. And another way is to use the output of the system in a particular task for your target audience. So with respect to the quality of the output, you can use some automatic evaluation metrics. And there has been many evaluation metrics that were used throughout the short history of text simplification. One metric, for example, one set of metrics concern readability. So you know that there are several indices, automatic indices, to compute the readability of a text. These are based on basic features, such as, for example, the average number of syllables, or the average number of words, or the length of the sentences, or the distribution of words in the text, and so on. Okay. So readability metrics have been used for assessing simplification, sometimes wrongly because they do it at the sentence level instead of doing it at the text level. And you can also use machine translation evaluation, because usually what you have when you evaluate the system is that you have the original text and then you have a gold or ideal simplification. So that means that when the system outputs some simplification, you can compare with the ideal simplification using, for example, metrics from machine translation, such as blur. But those metrics are not simplification specific, okay? So they are not actually measuring the quality of the simplification. That's why it's important to have human evaluation, yeah? So to give your output to your audience or to a set of human informants in order to measure how grammatical the text is, how the meaning has been preserved. So it's important that your output is simpler, but still you are transmitting the same content. Okay? And how simple is this content? Usually this is done with on a Likert scale with 1 to 5. So you ask how grammatical is this sentence, yeah, how simple is this sentence, and whether the sentence preserves the meaning when compared with the original. There are novel simplification metrics that came out. One is a simplification metric that combines readability with a metric that is used in paraphrase evaluation that is called iBlue, and this is called FK Blue. And there is another metric that is called SARI, which this metric looks not only to the gold standard simplification, but also to the source document or the source sentence. Okay? And also takes into account insertion of information, deletion of information, and preserving information. Okay? So it's more appropriate for simplification. It correlates much more with human informants. Then you may have also testing your simplification with users, with the real users, and you may give them the simplified text and compare how long they take to read the simplified text versus how long they take to read the original text. So this will be reading speed evaluation. Or you can give users the simplified text and ask a few questions and then count how many answers they get correct using the simplified version instead of the original version. And you can compare these numbers. Okay, so this is an example of quality evaluation by humans. So the first sentence is the original sentence. So you have grammaticality, meaning preservation, and simplicity score. So you can see the transformations that have been made on the sentences. So highlighted here are the words that were modified. So this is the original sentence. So you can see 3 systems and the scores that they get. And you can see that you can see this one that has selected this verb. Although it is just a simple replacement, it makes the sentence totally equivalent, yeah, preserves perfectly the meaning, is grammatical because there was very little modification. Okay. Instead, the last one is a system where you see noise was output while processing the text, so it gets very bad evaluation. Okay, so there has been, with respect to lexical simplification, there has been many approaches. So the first approach from 98, so very early system, was a rule-based system that used WordNet. Then a few years back, started to appear sentences based on the use of data available for simplification. I will describe Jatzar et al. A little bit later in a few slides, and Biran et al. Also in a few slides. So they use either simply English Wikipedia, or they use a combination of English Wikipedia and simple English Wikipedia. Then there are systems that learns transformations by looking at parallel data. Yeah? So, for example, looking at which alignments exist between a simple and an original text and its simplification. Then a system that Sanja will present. So the two systems are based on similar techniques using word embeddings, not relying on any lexical database in order to produce simplifications. And Gustavo Paetzold developed a quite interesting tool that is available that implements several lexical simplification algorithms. Okay, so that's quite useful for developing your own lexical simplification system. Okay, so the idea of rule-based lexical simplifications that you will try to induce from some data, some replacement. So replace the complex word A by the complex word lowercase a, yeah, in some linguistic contexts. So how you do that? So you could do learning rules from data. So one idea, for example, that is quite neat is that you could take, for example, simple Wikipedia and look at the edit histories of this resource. So you may isolate sentences that from one version, yeah, was transformed into this in another version. Yeah? So there is only one replacement here, so it replaces an expression here by another expression here. So you can assume, okay, this was done to make the sentence more readable or easier to read, okay? And you could have estimations of when this replacement is being made for making the text more simpler, okay? So you can, for example, estimate probabilities that this was done to make the text simpler, or you could estimate probabilities of this was done because there was a mistake in the sentence and I need to correct it, not to make it simple. So you can have a number of probabilities and then you can extract the most probable rules. And once you have that, I mean, the algorithm, what it produces is a list of replacements, okay? Not a simplification system, but a list of possible replacements, which can be compared to replacement learned or produced by humans. Another approach that is interesting is the use of simple Wikipedia and English normal Wikipedia, yeah, to try to identify first pairs of words which could be replaceable. So one word could be replaced by the other one in the same context. So in order to do that, what you do is to collect word vectors, the traditional word vectors, the discrete word vectors, and then by computing cosine similarity between all the words in English Wikipedia, you can say, okay, so the cosine similarity between these two words gives me a good cosine score. So I say these two words are replaceable in the same context, okay? And then you can use, for example, WordNet to filter, let's say, things which are not appropriate. So, for example, you could use WordNet to isolate things that are antonyms, because antonyms will be also appropriate or occur in the same context, but they are not appropriate for performing simplification. So, WordNet is useful to do this filtering. And then you have to decide, obviously, if these two words can be replaced one by the other one, so you need to know which one is the simpler one and which one is the complex one. So in order to do that, you can use frequencies computed in both simple Wikipedia and English Wikipedia, and combining that with also length, and that will give you a score that will say this actually is simpler than this one. Okay, so that's why the way in which you order the pair. And this approach also outputs a list of rules, but in addition to that, it also has a procedure to actually replace words in context, also by using the vectors. Okay, so syntactic simplification. So syntactic simplification, traditional approaches will have a set of rules to identify complex syntactic patterns in text, and then a set of procedures to use the match text to rewrite the sentences in some way. Okay? And there are data-driven systems that will learn the transformations automatically from, let's say, parsing trees or other structures. And then there are the neural machine translation systems that will try to learn everything in one go. Okay, so the first approaches obviously were very simple. So this is actually the first approach for text simplification, where the rules look like those. So very simple patterns where you may have literal, some literal elements, some variables, and then each rule will have a part that will be matched to the text, and then a part that will tell you how to transform the text. So it will be very, very easy to apply. So you match the text, the rule to the text, to instantiate the variables, and then you follow the procedure on the right-hand side in order to recreate your text. Obviously, it will have, will be probably precise, but will have very low coverage. I think I will skip this one. And on the same idea, so very early, so people decided that there should be a way to learn these rules instead of writing them manually, to learn them from data. So the same authors of the previous procedure decided that they will try to learn rules for sentences which contain relative clauses. So they have a bunch of relative clauses. They have a bunch of sentences with relative clauses and their simplifications. And what they did is to parse them, yeah, and then put them in some formalism. And then the simplification, also the sentences in the same formalism. And then they decided where the cutting and copying points, for example, to decide how to transform one sentence into the other one. Okay, so this was very early material, obviously only for relative clauses. Yeah, there was not enough data to do anything else. But later on, there were more sophisticated approaches in order to learn from parsing trees. So in 2010, we developed a system to learn from how to transform sentences from parsed sentences from English Wikipedia into sentences in simple English Wikipedia. So what they did is to align, although English Wikipedia and simple English Wikipedia are not translation one another, yeah, they are comparable corpora, they are not parallel data. So what they did is to extract from these two resources sentences which have certain degree of similarity. Okay? So they took these sentences with a certain degree of similarity, obviously from equivalent pages, yeah, and then they aligned them. And then they model certain replacements of in the parsing, certain syntactic operations on the parsing tree. So let's see what they did. So if this is the phrase structure of the sentence, so they would like to learn how to, for example, split this tree into two parts. Yeah? So coming from here, so they learn that they have to cut here the tree because they want to get to the sentence which is simplified. So they compute probabilities of which is the probability of cutting here or cutting there or cutting there. They will compute probabilities of copying subjects. Yeah? So in this case, copying parts of one tree into the other one. They will learn probabilities of deleting and reordering components, for example, in noun phrases. And they will learn probabilities of replacing some words by other words, lexical simplification. So this approach contains everything, contains syntactic simplification and lexical simplification as well. The question here is also that, I mean, we don't have perfect parsing trees. We don't have a curated data set that has the original text, which is manually parsed, and the simplified text, which is manually parsed. Yeah? So you need to create that data. So in order to do that, what you do, so you take the simplified, so you have to have the examples. Yeah? You have to have pairs of examples of this is one tree, this is the other tree, and what are the operations. So you have to simulate, create training data that simulates these operations, the copying, the splitting, the merge, the reordering, and so on. Okay? So you have to have a procedure to generate this data. And this approach is quite sophisticated, and when you see the evaluation of the approach, I mean, it was sad to see that systems that are not so sophisticated perform better than this one. So you have a whole apparatus to create simplification, but actually doesn't produce better output than other systems that are simpler. So Sanja developed a few years back also a method for simplification that is syntactic simplification, but based on information extraction. So she will tell us how this is done.
Let's try. So back in 2013, we knew already that there are these syntactic simplification systems that are mostly rule-based, like Horacio was saying until now. But as you saw, all these parse trees, they required lots of linguistic knowledge. It was not easy to go from one genre to another, from one language to another. Plus, if you have really complex sentence, then usually your parse tree is also not so perfect. So it had its flaws in this approach. On the other hand, we had at that time data-driven approaches. There was already English Wikipedia, Simple English Wikipedia, those phrase-based machine translation systems, but they were doing almost no changes. Here and there, they would replace one word with another, but that was all. And we saw that in all these projects that were going on at the time, you see that you have these news texts that are so complex, but there is lots of information that we really don't need from there. If you just want to have an idea what is happening, gist of the news, you don't need so much information. So at the time, you already had these event extraction systems that are working fairly well on the news text. So we said, okay, what if we use that to simplify text? So we will use already existing event extraction system. So we give the whole news article, apply event detection system. It points out these are the events here. And then from those, we generate simple sentences. Anything that was not captured by the event extraction system, it will disappear in the simplification. So in a way, you're doing at the same time simplification and summarization, because you're just keeping the main information there. As we were using this event extraction system, we were just keeping the information that we are certain of. So uncertain, negated things, they were avoided. And we had two different simplification schemes. So once we identified events, there are two possible ways. If I had one original sentence and I detected 3 events in it, I can just delete everything that is not part of event, but still make only one simple sentence out of it. Or I can do the event-wise simplification, where if I had the original sentence in which I identified 3 different events, I will make 3 simple sentences. Each event will be one simple sentence. So in that way, we are doing this sentence splitting that was before done with these rule-based systems. And to evaluate the system, we were using readability as an automatic way of measuring, because we are here doing simplification on a discourse level. We are taking the whole text. Event detection is done on the whole text. It's also making sure that the coreference is there, that he belongs to that person or the other one. And we also had a human evaluation. So to get an idea, so imagine that this is the text that you have. So this is one paragraph. So you have this guy, Libyan intelligence officer, who was convicted in bombing. He died in his home nearly 3 years after he was released from the prison. And there were some complications there. And what you see here in colors are the parts that are identified by the event extraction system. So in red, you see the subject, the one who is doing the event. In blue, you see the event. Green tells you when, and purple tells you where. And everything else that is not colored, this is what we want to eliminate. This is not essential for getting the story. So ideally, what we want is to go from here and get this guy convicted, bombing, died in his home, full stop. 3 years earlier, he was released from the prison. And this would be a nice way of simplifying and summarizing this text together. So as I said, we use the event extraction system. So the thing is, you can think of this approach as unsupervised in terms of text simplification. We don't need parallel data. We don't need original and simplified text. We have original text, apply event extraction, and generate simple sentences, unsupervised. But the event extraction system was supervised. Now, to be able to replicate this kind of simplification, you need event extraction system that works well for your language or your domain. That is your starting point. This event extraction system was only extracting factual events. So no negations, no uncertain events there. So as I said, it's a two-step process, supervised extraction of events, and then unsupervised these simplification schemes. So to demonstrate, here is the same sentence that you saw before. The second sentence is eliminated, the one that didn't have any events. So in a sentence-wise simplification, as I said, you're trying to remove everything here that is in gray as much as you can. There are some gray things here left because they need to be there for the grammaticality, for the fluency of the sentence. But everything is still kept in the same sentence. So this is a simplified sentence, has less information. It's shorter, but it's still everything in one sentence. While in the event-wise scheme, each event on its own got its sentence. Here you see that there is bombing and convicted, but we have one of the rules is that if you have these kind of events that cannot stand alone, they will still be kept in a sentence with the event that is preceding it. So here you have the simplification that is made of 3 shorter sentences. And this is the real example of the system, how it works. And on top of that, we also tried to do pronoun anaphora resolution. There is no consensus on should you do it or not, for which target users you need to resolve pronouns. So we just wanted to experiment with it. We had already a system for it, so why not? And as I said, we evaluated by using readability indices and also human evaluation. You saw before that human evaluation does evaluation of grammaticality, meaning preservation, and simplicity. Here we needed to slightly modify the definition, what is meaning preservation and what is simplicity. Why? Because we are deleting information. So for us here, for meaning preservation, the question was how much of the information that needs to be kept is really kept. And the simplicity meant how much information that can be deleted, that is not important, was actually deleted. And these two together, we called information relevance. So it was a harmonic mean of these two values. And as a baseline, we use something very basic. So we take we parse the sentence and then just keep the main clause of the sentence, thinking that that's probably the most important information in that sentence. Inter-annotator agreement, we had 3 annotators, was quite okay. I mean, for these kind of subjective tasks, these kappa scores are okay. Of course, for grammaticality, it's easier to decide, to agree on, than for meaning and simplicity, where you ask people this information that is important or that is not important, that's more subjective feeling for that. And as you can see here from the results, okay, we are better than the baselines, these systems. Grammaticality of the baseline system, this is the scale 1 to 3. So 3 is the best. Baseline, of course, has a very good grammaticality because it's the main clause of the sentence, so it shouldn't have problem with grammaticality. But you see that it's penalized here because it's often deleting information that it shouldn't delete. But then with respect to sentence-wise and event-wise schemes, you see when we keep all the information in one sentence, then grammaticality will be worse. Why? Because we are deleting information and then the fluency will be damaged there because it will be missing some conjunction or some short word there. But if you do the event-wise simplification, so each event becomes new sentence, then you don't have this problem. Each sentence will be fluent and grammatical on its own. So grammaticality is much better and relevance is slightly better. Pronominal anaphora didn't seem to make much difference on top of that. So maybe just to recap this part. So what we saw so far in text simplification, we generally have these two main tasks: lexical simplification or syntactic simplification. And as we said, ideally, we want to do it on a discourse level to also check the order of the sentences, cohesion and coherence in the text. But usually the systems that we have so far are just addressing lexical and syntactic simplification. As different kind of approaches, you saw supervised and unsupervised. Unsupervised ones usually have nicer output, more readable, better fluency, but they're time-consuming to make them because you need human expertise for rule-based systems, while the supervised ones usually have this problem that we don't have enough data, and that's why they're not performing very well. And as you saw from the evaluation, it's not an easy task here. How do you evaluate, is your text simplification system good? You need humans to evaluate it. You don't know, are they really? So if you're simplifying for people with some special needs, then maybe taking someone from the university who is non-native speaker or native speaker telling you if this is a simple output on a scale 1 to 5 is not actually a good proxy for your target users. Ideally, you want to check the usefulness, to do eye tracking studies on it. It's not done. And you have different kind of metrics that you can apply depending on what kind of simplification you do. Do you use machine translation evaluation metrics if you're borrowing their ideas, or you're using readability metrics, and so on. So I think now it's you.
Okay, now let me tell you about a few full projects. So we said that text simplification started as a pre-processing, as an idea of doing pre-processing for other natural language processing tasks, but then the interest on creating real systems for real people emerged, and there have been a few examples of those systems that we want to summarize here. So the PSET project was actually the first project for addressing people with special needs in simplification. So it was for English. It targeted people with aphasia. And the objectives were to try to replace pronouns by their antecedents, because they have problems, people with aphasia may have problems in recovering the antecedent of pronouns. They have problems with processing passive voice. So if you say the girl was kissed by the boy, so the person may not know who kissed who. Okay, so they need to write the standard order. And they have also problems with the lexicon. They may need to have words which are more frequent than words which are not very frequent. So for the NLP, so WordNet was the database used for recovering synonyms, for replacing the words. Frequency was the measure to be used to decide which word was easier than the synonym. And in order to deal with passive constructions, they use rule-based systems. So they use a parsing system and rules on top of it. The Por Simples project was for the Portuguese language. The special audience was people with low literacy, which this was for the Brazilian Portuguese language. And there is a huge problem of low literacy in Brazil, so there was a social project. And the objectives were mainly to try to reduce the complexity of the syntax of articles, newspaper articles. So the NLP that was involved here, it was a project based on the creation of a corpus, so has produced a corpus which is available for research, where you have I will describe it later, but you have original text and two simplified versions of the documents. So actually you can do quite a lot of research on that. And the system has some parsing or algorithms to deal with syntax. So they will have a cascade approach to resolve all the syntactic complexity and rewrite the sentences. Simplex was a project from this university where we targeted the Spanish language for people with intellectual disability, people with Down syndrome, and the objectives were to modify the lexicon of the system, of the text, so make it easier in terms of lexical simplification, and also simplify the syntactic constructions of the sentences. And the natural language processing that was involved also was a corpus-based approach. So we created a corpus that is also available for research of original and simplified texts. And based on the corpus study, we decided what needed to be simplified. We use word vectors, like one of the approaches in lexical simplification that I described, to model the semantic of the word. So these were discrete word vectors, not continuous word vectors. We use thesaurus available for Spanish that provide us with synonyms to make their appropriate replacements. For detecting complexity of different synonyms, we use a combination of frequency and length. And then we use a set of rules over dependency parse sentences in order to transform a complex sentence into simpler ones. The first project was an European project from the University of Wolverhampton and also other partners, and Sanja was involved in this project. Involved 3 different languages, Spanish, English, and Bulgarian. The target was people with autism, and the objective was to try to reduce the ambiguity of the text, try to cope with problems of figurative language by explaining the figurative language expressions or by replacing them, and then to make the syntax of the sentences simpler. And the NLP involved here was a set of techniques for dictionary lookup, so to search for expressions that are figurative, for example, and provide the appropriate explanation. The addition of images to the text to make the text easier to understand, and then rule-based systems to cope with the syntactic complexity. It must be said that this, the output of the system was not for the final users, but for the carriers of the text that could replace, could even modify even further the text in order to make it more accessible for the users. And finally, able to include is a project that we also developed here for 3 languages, Spanish, English, and Dutch. For Dutch, there was no simplification. Also for people with intellectual disability, and the objectives, again, as in Simplex, was to modify the lexicon, make the lexicon more accessible, and try to reduce the syntactic complexity of the sentence. And the approaches are very much like in Simplex. We use a thesaurus for finding synonyms, for replacing the lexicon. Again, word vectors, frequency, and length. Sorry, so I think only frequency and parsing rules. Okay, so also this project has the added value that some sentences were transformed into pictograms in order to make them accessible for people with more severe disabilities and who cannot read written text. Okay, so how an unsupervised lexical simplification system goes. So if you have a sentence like this, the sentence will be analyzed depending on what you want to achieve. The analysis can be deep or can be shallow. For example, here you can have just part of a speech tags for each word. Then there will be a process of complex word identification. So for example, these 2 words will be identified as complex because their frequency is too low or because they have some characteristics in some psycholinguistic database that make them difficult to understand. Then what we will do is to try to find simple synonyms. So if we use WordNet for automobile, you will have a list of synonyms. So automobile is not ambiguous in WordNet. If you have repair in WordNet, you will have several lists of synonyms depending on the meaning of repair. Then you will need a process of word sense disambiguation. So selecting which list of synonyms is the most appropriate for the word. So for automobile, you don't need any disambiguation, but for repair, you need to select the right meaning. And then you will need to select from the list the most appropriate word. So in this case, for example, the word fix, and for automobile, the word car. And then you will regenerate the sentence like this, and you will get a simpler sentence. So this approach is more or less a typical approach in rule-based or unsupervised lexical simplification. So with respect to context replacement, so you have to be careful depending on the language that you treat, because obviously if you replace a word, you may need to also make modifications. So you may replace by a synonym. So in the original it was masculine, and you replace by a feminine, or you need to rearrange the context. So these things should be taken into consideration. Okay. So and actually for able to include, we did something to try to solve this issue, try to generate the appropriate form and also to correct the context. For lexical syntactic simplification, so you do also text analysis. In this case, can be a little bit more complicated. So because you may need to recover the dependencies between the different words in the sentence. Okay, so you may use some simplification grammar in order to detect complex linguistic phenomena. So for example, main clauses and relative clauses, or main clauses and subordination, or the two parts of coordination, and so on. And once you have the different elements of the sentence, you may regenerate sentences using some text-to-text procedure. So you will have, in this case, two sentences that hopefully will be easier to read. And within the sentence generation process, you have decided already how to sort or order the sentences to make them readable. Okay, so a pipeline for full text simplification using a combination of rule-based system and some dictionary or corpus-based approaches will be like this. So you start with the text analysis, you detect complex words, so you perform word sense disambiguation to select the correct meaning of the word in context, and therefore the list of synonyms. You rank the synonyms to select the best one, and then you replace the original word by the simpler synonym, and then you do the syntactic simplification. So you parse, maybe you enrich the sentence again with dependency parsing, you apply your rules, you transform the sentences, and once you have new sentences, you go into the loop again, because they might need to get simplified again and again, okay? And the examples of the poem was composed by the renowned artist could be transformed in this way into the famous artist wrote the poem, where you have both lexical and syntactic simplification. So a few words being replaced and the passive voice being put in active voice. Okay, so simplification projects usually have a target population that this is very useful, because you know which phenomena you have to cover, and also because you have users to test, probably to test your system and to give you some, probably not them, but how they use the output could be informative for you. Although it is very expensive to run experiments with the users. So it's very difficult to run experiments of the users. So you may have in your whole project, maybe a few times you can have access to your final users. It's also very important to have other metrics to evaluate, like the traditional metrics that we mentioned before. Yeah, so, and these projects are usually characterized by their multidisciplinary aspect. Yeah, because you need probably people who know about the disability of the person involved, or people who will know how to simplify text, which are not computational linguists, but people from linguistics or people who work on easy-to-text projects and so on. For simplification, one very important aspect is to have access to resources in order to train or evaluate your systems, and we will present here a summary of resources available. So what are resources here? So you may need resources for lexical simplifications, such as inventories of synonyms. So you know you have WordNet and also the multilingual central repository that connects the English WordNet with several other WordNets. So this is very important. But also you have available several thesauros that are in English, in Catalan, in Spanish, and so on, that you can use. They don't come with definitions of the words, but they come with a list of synonyms. The downside of these resources is that they are crowdsourced resources. So people contribute to those resources. So the quality might be in question. Okay, so this is not like WordNet. Yeah, so for some languages you may have resources that are a little bit noisy. Yeah, I have to cut now. Okay, so so maybe we do a break here. Okay, sorry. So Sanja tells me that we need to do a break now. I don't know how long, 5 minutes or?
Yeah, just a bit. And then
yeah, 5 minutes maybe. Yeah, and then we continue. Yeah. Okay. Sorry. Okay, so in addition to this list of synonyms that you may need, and also you may need psycholinguistic data sets, such as a list of words by their difficulty, yeah, Coursera-Francis list of age of acquisition, and also comparable corpora. And several of them are going to be described very, very briefly, okay, because we need to move. So there was one data set based on the Semeval lexical substitution task that was transformed into lexical simplification task that was run by Lucia Spezia and colleagues. So the idea is that you have a sentence, and then you have a particular word that needs to be simplified. You have a number of substitutes, and then the goal annotation will sort these substitutes by complexity. So from the simpler to the more complex. Okay, so this is one data set, and there you have the statistics of the data set. Then in the over the similar data set, this resource was created by the builder. So where you have sentences, so you have here 2 examples of the same word. Yeah? So for example, acquires here. And for this one here, the analyst acquires knowledge. So you have this possible set of substitutions. So you have one cluster where all these are equally simpler, and then these are equally simpler, and these are equally simpler. Okay? And you can see immediately that the second version of acquire here has a different ranking, okay? Because it depends on the context. Okay, so this is quite useful as well. Then you have a data set that was created by Horn by doing crowdsourcing, where you have a sentence, and then you have a particular keyword here, yeah? And you ask 50 people which replacement they will provide for that particular word, and they collect all this information, and then they say, for example, 24 people said that events goes well here for supernatural events or paranormal phenomena, okay? 24 people said that, okay? And there are several synonyms with just one occurrence. Then a resource that was created here at UPF that is called Casas, where you have, this is for Spanish, that was created from the Spanish Open Thesaurus that we mentioned before, and also from the Google Books Ngrams corpus. So you have context here, and then you have a particular target word that should fit here, and then you have possible replacements. These come from the thesaurus, so words which are more or less equivalent to ámbitos, okay, and there could be easier replacements if you find them in this context. So the context is syntactic, not semantic, okay? Then you have this traditional data set, the Simple English Wikipedia data set that was created from original Wikipedia and Simple English Wikipedia, where sentences were aligned, yeah, and you have pairs of sentences. Yeah, it could be just one sentence or a pair of sentences and so on. The problem with this dataset is not very representative, so Sanja will tell us something about that. For example, this type of sentences, April is the 4 months of the year in the Gregorian calendar. You will have many examples of those in the dataset, so it's not very representative, so it's not very useful. So we developed for the Simplex project the corpus also for Spanish, where you have original sentences under simplifications. The simplifications were produced by trained editors, and you see in this corpus some superficial transformations, but also very paraphrastic transformations. Okay, so very complex replacements and transformations. And this is the Port Simplex corpus, developing the Port Simplex project, where you have newspaper articles. Well, this is one sentence. And then you have two ways in which can be simplified: a natural simplification, yeah, and then what they call a strong simplification. So the natural simplification is the editor can follow or not the rules that have been set to simplify the text, and this is a strict application of the rules. Okay, okay. And Sanja will continue now on with other data sets and other approaches.
Okay. So there were also several shared tasks in the last few years that are good resource for text simplification data sets and resources. So we had this shared task that we mentioned before, the English lexical simplification shared task. So you have a target word, and then you have 4 synonyms, and you need to order them from the simplest to more complex one. Then we had a shared task on quality assessment for text simplification. So in this one, we were targeting that human evaluation that you saw before, that we ask humans to rate simplification on scales from 1 to 5 for grammaticality, meaning preservation, and simplicity. So we used a data set of like 600 sentences, human evaluated, and then we asked teams to participate to try to do this automatically. So given the original sentence and the simplified sentence, rate on a scale 1 to 5, or I think in this task was actually on a scale 1 to 3, because we merged 1 and 2 as bad simplification, 3 was okay simplification, 4 and 5 was good simplification, and we said, can you do this automatically? And the best systems are not that good. So it's still this automatic way of evaluating the quality of the output of text simplification is not good enough, but at least we have some data set so that we can try to build better systems. And then in 2016 was the first shared task on complex word identification. So it was just for English. You had a sentence, the target word, and the question is this word complex or not for a non-native English speaker? And so this is also a large data set for complex word identification. The problem with that one was that it's just for English, it's just for non-native speakers, and also the number of people evaluating. So the gold standard was done just with the several people annotating that. So in 2018, what we did, we offered another complex word identification shared task, but here we had 20 annotators per each sentence, per each target word, and always we had 10 native and 10 non-native speakers. So we also tried to address this problem of not having the same needs for people who are native or non-native speakers. And we did it for English, Spanish, and German. And then the test set was also for French, because we asked people not only to make systems for one language, but also that you can use for training the data that you have in English, Spanish, and German, and then test it on French. So to build a complex word identification system for French, use what is given in another language. And you would be surprised how good are these results. So actually, you can use data set in one language and port it to another one, because usually they're using vector spaces, and these things port very well from one language to another. And then the corpus that is currently mostly used for text simplification because it's the biggest parallel data set with the good quality control is this Newsela corpus, which exists for English and for Spanish. It's bigger for English. In English, it has around 2,000 articles, news articles, that are then simplified to 4 simpler versions. So simplifying a little bit and then a little bit more, and the 5th version is very simple language. So you have around 2,000 articles for English and 250 articles for Spanish. And also what is interesting, those 250 articles for Spanish, they're talking about the same subjects as some portion of the English data set. So you also have it kind of parallel in 2 languages. What is nice about this one, it's a good quality control, it's trained human editors, it's an American company who makes money out of this. And they offer this data set for research purposes. You get it in a document-aligned format. The bad side is you cannot release this data set officially. You cannot release the models that are trained on it. But you can see how different it makes in data-driven text simplification if you start from English Wikipedia, simple English Wikipedia, or if you start from really controlled quality data sets. So yes, it's freely available, but just for research purposes. So here you see you would have original article and then the simplification. So the last one would really have short sentences. So there is also some content is getting deleted there. But as I said, you are offered this corpus in document-aligned format, which is also a case if you want to collect such data sets from internet. You might find news articles on the internet that are original ones. You can also find independently written news articles that are easy to read. So you always kind of start from this document-aligned corpora, but now what we need for simplification, as you saw, it's usually we need it sentence-aligned. So Shu and her colleagues, they manually aligned some part of Newsela corpora. So upon request, you can get that from her. But we also developed 2 different systems for automatically aligning this corpora on sentence level for English, and also our systems we try to apply it for the Spanish part of Newsela, and it works fairly well. Cautious here. If you go from a level 0 to 1, 0 to 2, it works very, very well. When you try to align sentences from 0 to 4, it will have much more errors. So 0 to 1, it's like 98% accuracy of this alignment, but if you go from 0 to 4, you will have around 55, maybe. So maybe you need to filter out which kind of sentences you want to keep from there. So these are the pointers for the tools. Our tool have different kinds of similarity measures. You can have different kind of alignment strategies. So you can suppose that the order of information in the simplified version is the same as the order of information in the original text, but you might not do this. So you can choose which of these techniques you want to use. And then Gustavo has similar system for aligning Newsela. So to recap this part, there are lots of linguistic resources for many languages. But there are very few resources that are parallel data for text simplification, parallel or comparable. Even comparable is difficult to find. So you have to choose from, there are really good quality parallel data also from Simplex project, from Poor Simplex, from First project, but these are around 2,000 sentence pairs or something like that. But if you want bigger data sets, parallel data sets, you have to deal with English Wikipedia, simple English Wikipedia, where there you have no quality control over the simplifications, and you also have the problem with automatic alignment of sentences. And this parallel data, I mean, we are having problems even with English, Italian, and Spanish, where there is some data, they are small. For other languages, there are absolutely no parallel data for text simplification. So now, probably the most novel things now, you would be surprised, these neural approaches, I'm talking about state of the art, but you will see I'm talking about lexical simplification from 2015. There were not much more things done for purely lexical simplification since then. So at that time, there was this big thing of everybody uses word embeddings. They just appeared. It's a great thing. We can use it for different things. So we thought, OK, so what we have problem here for lexical simplification, you saw how the rule-based lexical simplification functions. So you find the target word. You go somewhere to search for the synonyms. For example, you go to WordNet. Then you need to rank the synonyms. And then you need to substitute them. The problem is WordNet does not have such a great coverage. And in general, in text simplification, coverage is a big problem because those things that you want to simplify, they're usually infrequent. So it's very likely that they will not be there in these resources that you are using. So we said, OK, it's difficult to do this supervised. But now we have word embeddings. And once we port the word in this vector space, we can retrieve synonyms for any word, because now instead of using WordNet, we're going to find words that have a good similarity to this original vector. So practically, we are just using cosine similarity between the two words, and that's our proxy for the similarity of the words. So in this approach, we don't need any parallel data, any simplified data. So we operate completely on the original text. And therefore, it will cover better coverage than other lexical simplification systems up to that point. The problems with this kind of approach is we are simplifying only single words. We don't simplify longer phrases, no multi-word expressions, so just isolated words. And another big problem at that time, 2015, was the problem with antonyms. It was a problem with word embeddings that bad and good and cold and hot, they're very close in those vector spaces because they are appearing in a similar context. So what is the main idea? That simple words, so in which we want to translate complex words, they're not only appearing in simple corpora, they're also appearing in normal text, probably with a very high frequency. So what we need a good semantic similarity measure, so for each word, so that we can find synonyms. And then a good measure of word complexity. So once we have substitution candidates, to know how to rank them, how to choose the one with which we want to replace the original word. So for that, we didn't have this first step. Remember, Horacio was talking about this all-in-one systems and modular approach. In modular approach, you have first the system that searches for complex word that they want to replace. In this approach, we skip that step. We don't have this step-by-step procedure. It's all together. So we focus on all content words in a given sentence and try for all of them, we will find the substitution candidates. We will rank them. And then if we find something that is close enough and simpler, we will replace it. If we don't find, if other things that we find are more complex, then we won't replace them. So we don't have specific complex word identification, but it's done inside actually by the ranking function. So we focus on content words. For each content word, we retrieve the closest word embeddings and take the 10 most similar ones. We are avoiding morphological variance, of course. And then we rank those candidates based on three things. Of context similarity. So in a symmetric window of size 3, we are checking the cosine similarity of the target word with all the nearby words. We check the simplicity. For this, we were using frequency in a large corpora. If you want to adapt it for different kind of application, you probably need to change this. So if somebody has problem with frequent words, then this is your simplicity metric. If somebody has a problem with ambiguous words, then you will have a different simplicity metric, so on. And in the end, we also have fluency there is an important thing. So practically, can this word replace the other one and still have a good fluency? So for that, we use language models. And to evaluate it, we tried on the replacement task. So the one that you saw where you have a sentence from Wikipedia, target word, and then 50 people were asked with which one they want to replace it to make it simpler. So we tried our system on that task and also on the ranking task. So the one that you had a target word and 4 possible synonyms, and you need to rank them from simplest to most complex. So that was in terms of how good it is for different applications. And then to also evaluate how the output sentences are. Because one thing is, yes, this word is simpler than this one, but how it fits the context, for that we needed a human evaluation. So the standard way of doing it on a 1 to 5 scale, we checked grammaticality, meaning preservation, and simplicity. And then we compared with previous systems. So you saw this is the unsupervised system based on Wikipedia edit histories. And then this is the supervised system that is taking English Wikipedia sentence align corpus and then using Giza++ aligning words from original and simple Wikipedia and making the supervised lexical simplification system. So this was the state of the art before, but supervised. And this is our system that is unsupervised. And the biggest difference is actually in the number of changed words there. So if you look here, unsupervised system rarely changes anything. This is what we said. There is a problem of coverage of unsupervised systems because if you're looking just in WordNet, you might not find any substitution candidates. So our system performs almost as well or similar to the supervised system, but this is also kind of unfair comparison because the test set is Wikipedia sentences, and this supervised system was trained on exactly Wikipedia. Our system is not trained on Wikipedia. The word embeddings that we are using are news articles. So actually, you see that although it's unsupervised, it performs well on a different domain, which probably wouldn't be the case with a supervised system here. And on the ranking task, also we saw that we outperform with our system the winner system of this competition. And with respect to the human evaluation, there was something very interesting here that draw our attention to. So here are the results of the unsupervised system and the previous unsupervised system based on edit histories. And this is our system. So you have here grammaticality, simplicity, meaning preservation, and this is the percentage of sentences that had at least one change after going through this system. So what you see here is that our system has much better coverage. This evaluation here is done on all the test sentences. And you would say these two systems perform similarly. See, the grammaticality here is similar. Okay, simplicity is slightly better for our system, but meaning preservation is better for this unsupervised system. But what is happening here? We are taking into account all the sentences, and more than 80% of them had no change at all. If the sentence was not changed, of course, it has a perfect meaning preservation score. And of course, it has a perfect grammaticality score. So here you see the results. If you just compare the two systems on those sentences where both systems perform at least one change. So you see, when actually this system is making some changes, it also often makes some grammatical errors and doesn't change meaning a little bit, and also it doesn't simplify it as much as this system. And this is a very important thing to remember when you compare many different text simplification systems, that it makes a big difference in these numbers depending on do you filter out sentences in which systems don't do anything, because if you compare a system that rarely does any change, it's going to give you very high meaning preservation and grammaticality scores, but this system is not actually useful. So here is an example of original sentence. This is the output of the unsupervised system, the one based on edit histories. And this is the output of our system based on word embeddings, that is unsupervised. And as you can see, this system just made one change, and it was actually not correct change. And our system made 3 different changes. 2 were okay, we could say. But this is what I said before, problem with word embeddings. The word refused and the word asked will be very close in this vector space, although they have a very different meaning. So this was done in 2015. Now word embeddings are also getting better, so who knows, maybe with the new things, this could work better. So a year later, Gustavo and Lucia had very similar system for lexical simplification. So kind of at the same time, we got to the idea of let's try to use the word embeddings. The difference is that they had context-aware word embeddings, so they used part of speech tag there as well. And they used the modular approach, so they had a separate module for complex word identification, retrieving substitution candidates, ranking, and so on. And for word embeddings, they used the corpus of movie subtitles, not news articles as we did. And then if you check the results, they're kind of performing similarly. So that was just the lexical simplification done using word embeddings. But then in 2017, there was already so much work done on neural machine translation. And there is OpenNMT, so there are open source things for doing neural machine translation. So we said before, people were using Moses and phrase-based machine translation for simplification. And that was not making too many changes in our case. But let's see now what happens if we use neural machine translation. If it works so much better for neural machine translation, maybe it will work better for text simplification. So that was the first attempt to use sequence-to-sequence neural networks for text simplification. So you give it the whole sentence and get as an output the whole sentence. It's not any more isolated changes as in the system before. And this model can simultaneously perform lexical simplification and content reduction. Why is it doing content reduction? I will show in a bit that this Wikipedia parallel data that we use is not this old one from Kauchak, where the sentences you just have, if they are over a high threshold, that they have a similar meaning. But there is a newer version of sentence-aligned English Wikipedia and simple English Wikipedia that covers both like full matches, full meaning preservation match, and partial matches. So those partial matches are actually really good for modeling content reduction here. What is interesting to see is that while those phrase-based text simplification system using Moses, they had problem whenever they make changes, they would often have bad grammaticality and meaning preservation. With neural systems, grammaticality and meaning preservation is practically perfect. So that's a big plus of neural machine translation. And we also saw that they achieve higher level of simplification than the state-of-the-art text simplification systems that are not neural. And this is probably just because they make much less errors. It's not that they do so much more changes, but when they change something, they do it well. So as I said, for the data set, we use the newer version of sentence-aligned English Wikipedia and simple English Wikipedia. So there you have around 150,000 full matches and 130,000 partial matches. And then we used for hyperparameter tuning for our system, for the text simplification hyperparameter tuning. I will show it in a bit what I mean by that. we use this data set that Shu and her colleagues made in 2016. So these are 2,000 for tuning and 359 sentences for testing. So these are sentences from Wikipedia that were given, each one to 8 human annotators, to make a simpler version of that sentence. They were focusing on lexical simplification, so not syntactic, but lexical. But the point is that these are very good because we don't have just one gold standard for each sentence, but 8 different gold standards, which is really important if your tuning metrics are blue or meteor or something like that, because they work much better if you have multiple references and not only one. What is the challenge with this data set? Because it's Wikipedia articles, there is a high number of name entities and very high lexical richness, which we know that for neural machine translation is a tricky point because you need to have lower amount of words in your vocabulary. So here's an example, what I mean by full and partial matches. You will see that the first example has completely the same information contained in original and simpler version, while here you have some partial overlap of the meaning. And that's what allows us to have the system that also learns these types of transformations. If you would feed the system just with full matches, then you probably would not have this content reduction in your output. So I wouldn't go now into the details of the system because we just use the OpenNMT framework, 2 LSTM layers, nothing new in this part, OpenNMT as it was there. And you actually have all these details on our GitHub page, so it's fully replicable. And this is not, I think, most interesting part here, nothing new in this part in comparison to machine translation. But what is new? If you would use just those parameters and neural machine translation as it is, what we see in the output as a best hypothesis chosen by the system, most of the cases nothing was changing. Because these systems are made for machine translation. They're trying to preserve the meaning as much as they can and to be close to the target as much as they can. So how we made the system do well for text simplification? First trick, word embeddings. In machine translation, what you have, you train word embeddings on your source side from the source data and on your target side from your target data. But here for the simplified text, we don't have so much data. So what we do, we borrow the idea from Kauchuk that was done for phrase-based machine translation. There you had language models, and he saw if you increase the amount of data in your corpus for training language model, so for the simplified version, you don't train the language model just on the simplified text, but you add some portion of original text, the system works better. So we said, let's do the same here. So on the encoder side, we had word embeddings over original English plus the Google News. On the decoder side, we didn't have just simplified English, but we also had a portion of original data, original language. And then, of course, we had to deal with out-of-vocabulary words, but again, this is nothing new. This is standard procedure, what we would do in machine translation as well, replace them, and then taking stuff from the attention layer to retrieve the original words. Now, another trick. So the trick number 1 was word embeddings. The trick number 2 is default output is not the best for text simplification because the tuning inside is not made for text simplification. So what we try to check is what would be the best beam size. So we experimented from all beam sizes from 5 to 12, and also which hypothesis is the best. So you can let the system give you the default best hypothesis that is ranked number 1 by the system, but you can also retrieve a larger list of hypotheses that the system provides. And we saw that if we focus on the first 4 hypotheses, the system gives us the second and third look like the best simplifications. They do enough. They don't damage the output too much. If you go lower, if you take the 9th or 10th hypothesis, they're changing a lot, but they're also damaging the output. So what we wanted to see is how to find the best beam size and best hypothesis there. For that, we use the development data set from Shu, as I said, these 2,000 sentence pairs. We applied the blue metric and this SARI metric that you heard before, that it's a text simplification metric. So it's not just comparing with the target gold standard, but also that it's different enough from the original. So this one favorizes changes. This one ensures fluency. So we tried with both of them. We applied them on the development data set, and then we choose the beam size and the hypothesis, which in majority of the cases is the closest to the gold standard. And then we do the human evaluation. Well, we have some automatic evaluation, but it's more for reporting numbers and see how that correlates with the human evaluation. But this is the main thing. So we check the number of changes. Are these changes correct? Change is correct if it's simpler, and if the grammaticality and meaning preservation are good. And then we have grammaticality and meaning preservation 1 to 5 scale, as usual. But for simplicity, we decided not to use this 1 to 5 level scale. Because what we saw before, you ask humans to say, is it simple to give the simplicity score from 1 to 5? What is for me 2, for somebody else might be 4. It's very subjective feeling if you give the absolute scale. So we said instead of that, we always give them a pair of sentences. There is original and a simple sentence in a random order, so they don't know which one is which one. And then we ask them, is the left sentence much easier to understand than the one on the right? Is it easier to understand? Are they equally difficult to understand? This one is more difficult, this one is much more difficult. So we ask them on the semantic scale, but later we transform this into numbers from -2 to +2. So then we compare such system with state-of-the-art systems. Why I say state-of-the-art systems? Because they have such different architectures, they have different target groups or applications, so you cannot say one is better than the other, but they're very different, so we take the best of each. The first one is syntactic-based machine translation that was used in 2016. This is the one that I was explaining before, lexical simplification using word embeddings. This is using phrase-based machine translation, so Moses, with re-ranking of the output. So same idea as we had, let's not take the best hypothesis that the system gives, but we will re-rank them. People were before doing for phrase-based machine translation, so we compared also with that system. And for all of these, we were not replicating, we simply got the output from their system, so make sure that it's the best output they can get. So what we found here, narrow text simplification models have higher percentage of correct changes, and they have more simplified output. What you would see, there was a big table, and in paper it's a huge table with lots of numbers. So on this relative scale for simplicity, so it goes from -2 to 2, the state-of-the-art systems are all around 0, slightly in the plus. Because when you do one lexical change, when you ask people to do it on an absolute scale, they might prefer one than the other. But when you show them these two sentences and ask, is this one much simpler than this one? They say it's not. They don't even notice that there is some slight change there, because if it wasn't not difficult at the first place, the simplification doesn't help. So what you saw in this relative simplicity comparison, that state-of-the-art is around 0, and these systems are close to 1. So they're still not doing much more, but they're better in that sense. And then the trick with the word embeddings and with then SARI inside to find the best beam size and the best hypothesis was something that helped that we have higher number of changes and higher number of correct changes, that it's very simple, and that we have a good grammaticality and meaning preservation scores. So what is most important, depending on which function you use for tuning, so if you use SARI, you will have higher number of changes, which is what you would expect because this function favorizes changes. And if you rank the predictions with blue, then you have the highest number of correct changes because it's making sure that it's closest to the gold standard, so to preserve fluency. So you might have less changes, but they will be more correct. And then if you use customized word embeddings in combination with the SARI for re-ranking, that's how we get the best systems in this neural architecture. So here is one example. This is the original sentence from Wikipedia. As you see, very long with lots of information. And this is the output of our best system. So it somehow find out that this guy pinned Guerrero, and that's how he win the championship. So grammatical meaning is there, the most important. Of course, it's cherry-picked, but still shows you well that grammaticality and meaning preservations are not problem, but this one also shorten it very well. So to recap this part on neural text simplification, so in comparison to the non-neural simplification systems, they generate much better, much more grammatical output. They preserve the meaning well. They lead to more changes on average and higher percentage of correct changes. But other people who tried using neural machine translation but without the tricks for word embeddings and for re-ranking, they said that they don't work. So you cannot just port things from machine translation without any adaptation. So you need to do some tricks that are important so that you force actually text simplification. And the other thing that we find out from evaluating these systems, as you saw, we had different evaluation scores: grammaticality, meaning preservation, simplicity, number of changes, number of correct changes. And now when you have different configurations of your system and you compare them, one is winning on one evaluation metric, the other one is winning on the other evaluation metric. So how you would decide that which one is the best? Well, that will depend on your target population or your target application. Because, for example, if you simplify for non-native speakers, you don't care if it's not really grammatical, if the point is that they just need to understand the text, what is there. But if you're simplifying for someone with cognitive disability, then you maybe want to make sure that it's as simple as possible, and so on. So which one evaluation metrics you want to use depends what is your final goal. So just very briefly at the end, so you get an idea where we are at the moment with text simplification, what we can do automatically. So for the fully fledged system, when I say fully fledged, I mean it does syntactic simplification and lexical simplification. And additionally could be content reduction. For these, we don't have fully neural systems. Because this is what I showed from machine translation. You saw it can do content reduction and lexical simplification, but it doesn't do syntactic simplification, reordering of sentence parts, or splitting sentence. So we compared just those systems that do syntactic and lexical simplification. So there were practically these two systems before. So this one is a supervised system based on English Wikipedia and Simple English Wikipedia in 2011. This one is a hybrid system that uses data-driven lexical simplification and rule-based syntactic simplification that was state-of-the-art for a long time, I think even still. And these two systems, EvLex and LexEv, are combinations of the two systems that I was showing you before. So event-based text simplification, the one that was doing event detection and then chopping sentences, making short ones. So that one does syntactic simplification. And the other one with the word embeddings that does lexical simplification. So we combine these two together to get a fully fledged system. And you can combine it in two ways. You can first apply syntactic simplification, so event simplify, and then the lexical, or you can do it the other way around. We were not sure whether the order would matter, so we experimented with the both. So you see here at the top, you see the original sentence. And this sentence was not changed by these other two systems, but our system made one lexical change and shortened the sentence. Then you have another original sentence where one of the systems, the supervised one, didn't do anything. Their supervised systems rarely do sentence splitting because they don't have enough data in the training data. But the hybrid one that has rule-based syntactic simplification, it does this reordering. It always says who said what, puts who said at the beginning of the sentence. This is what you see here. And our system makes two sentences out of this and makes one lexical simplification. Then if you have another long sentence there, what these two systems will do, they do syntactic simplification. They both split into two sentences. This one also does reordering to say who said what at the beginning. Our system just changes, does one lexical simplification, and it also does content reduction. Because here you see the sentence says that the ambassador's arrival has not been announced and he flew in complete secrecy. So for our system that has event detection, these are two practically same events. The ambassador arrived and that was not announced, and he flew in complete secrecy. So it just decides to show once this event. So finally, to summarize what we saw here today, we saw that text simplification is a very complex task, and it needs a lot of linguistic and real-world knowledge to be applied correctly. And automatic text simplification has a really good potential to serve everybody, so people with special needs, but also as a pre-processing step for various NLP applications. But it's not perfect yet. It's not still in that stage to be completely automatically used. It usually needs some post-editing. There were various techniques that we used in the past for text simplification. So we have rule-based systems, unsupervised, supervised, borrowing techniques from machine translation, and so on. They all depend on which language you're addressing, which genre. Do you have data? Do you not have data? For whom you're simplifying? And at the moment, probably the biggest problem with text simplification is that it's not done on a discourse level. So we do this on a sentence level or word level, but then if you give the whole text to the system and it does this simplification on sentences, very often you lose the cohesion of the text. And that's something that hasn't been addressed enough so far. So we could say that there is much more to be done still for text simplification to take it to the next level of working on the discourse level and also being able to be applied completely automatically. That's all. Questions? Questions, comments, suggestions? Yes? We need to give you the microphone, was it?
Thank you very much for the whole tutorial. If you finished with discourse, could you please suggest some data sets to train discourse models or some resources, how to address this problem?
So far from the stuff that are being used, I think only Newsela actually gives you the chance, as a big data set that gives you a chance for some discourse simplification, because they go from the whole text and then it's simplified in different levels. With Wikipedia dataset, you cannot do that. I mean, you have the dataset of original Wikipedia articles and simplified Wikipedia articles, but they are usually written independently. We don't know, is the simplification done by looking at the original article and it's simplified, or it was written completely independently. So actually what you're sure of, kind of sure of, because it's automatical alignment, is a sentence alignment, but not really on the textual level. And I guess if you take Simplex data set or first data set, they would also have simplification on discourse level, but they're much smaller. They're a few thousand sentences aligned. So that's the problem. Depends on how much data you need.
But it will be interesting to see in those corpora how these phenomena are addressed. How, for example, will be interesting to see how pronominal coreference is solved, whether, so a phenomena that you see very frequently in simplification, in text simplification for people with special needs, is that, for example, the referent is always rephrased in full form. So that's quite an important aspect. That's one phenomena for addressing discourse simplification. Also connectives, so Siddhartha was studying the problem of which connectives you will use. There are some connectives which are preferred over others to make the text simpler at the discourse label. So
there you usually have a trade-off, because when you start splitting sentences, they're simpler each one on its own, but you might lose the idea, is this something that is a cause and that is effect, and so on. So it depends for whom you're simplifying, what is your goal you should address in one way or another.
When you said that you have to do some tuning for the RNN model, in the case of text simplification, you changed the word embedding pre-trained model, right? You used Google News. What other tuning should we consider?
So
is it just the pre-trained models, or are there other things?
So the main point is that if you just take the output hypothesis suggested by the system, that's not the best one, because it will usually be without any kind of changes. So tuning, in a sense, how to retrieve the best hypothesis, output hypothesis from all those that the system gives you, because the best ones are somewhere in the middle. It has to do some changes, but not to damage too much. I think ideally what you want is a function for this re-ranking, but which can be done in prediction time. We don't have such things, so we had to use the tuning data set and using Sari and Blue to try to find the exact beam size that gives the better results and which hypothesis. But that's probably the most important thing if you go from machine translation to the neural one at the moment, to the neural text simplification.
Okay, a naive question maybe. To back up this sort of solution, what sort of technologies could be used in a low scale? I mean, all those data sets, all those use libraries can be developed using, for example, Python, or would there be any other preference for, I'd say, for an exploratory or development tool set? Which would be the best approach research like?
I think
that now, I mean, these neural translation models, you can have them in several flavors, so but probably Python will be a choice for if you want to start developing something. So, but obviously, older tools may be in other different languages, so we have developed things in Java, for example. But I think that if you go for the neural thing, Python will be your choice. Okay. Yeah, I am assuming that.
for
yeah.
neural stuff, mostly it's used Python, but then for rule-based systems, that would be
Yeah, that's-
trickier.
Okay.
So it depends which way you want to go.
And there might be also some resources that you will need to integrate that are not in Python. But for example, maybe you have a fantastic parser in another programming language that you want to integrate because it's better. And but I mean, these should be also only integration issues. But I would say Python, fine.
Is there any simple demo already available to test the system and be able to, I don't know, even to participate in the evaluation? I mean, are there any web apps already
Yeah, we
doing
have,
these sort
yeah.
of things? Like,
Well, I mean, the apps that we develop for Simplex and for Able to Include, they're available. So I didn't show them here, but they are available. Where you can, it's a simplification portal where you put a sentence, click simplify, and then will appear the simplified sentence. So we didn't have time to show it here, but it's available. So if you send me a message, I will give you the links and yeah.
yeah,
Or I can put it at the end of the tutorial, and so the material will be available. I will give it to Aurelio, and he will upload these slides, and you will be able to play with them.
And also for other systems, you maybe don't have the demo. So for all the lexical simplification systems, you saw that there was a link. Gustavo made implementation of them. So if you run them, you can see how different lexical simplification work. Neural system is also fully available to download also the output of the systems. Also, LREC is gonna run shared task on reproducibility in 2020. So, for example, one of the things that we offered is this neural text simplification system. So there will be output, and then people will try to reproduce the human evaluation scores. If you're more interested in the human evaluation, there will be a nice challenge to try.
okay, well, thank you very much. It's a really challenging topic, and I guess that for everyone, I think in many times we face this need to have a simplified content because we're struggling trying to understand the signification of what we're reading. So it's super interesting. Thank you very much.